So, so dear participants, we are very happy that today we have two expert speakers. We have two speakers, very expert speakers. The first one is Mr. Ashunindu Mondal, our respected coordinator of this course, followed by Mr. Bishwajit Shon, Assistant Vice President, Reliance Industries Limited, in the section of Reliance R&D. So already we have seen that Mr. Mondal, he has got a very, very long innings with lots of credentials. He was a former Chief General Manager, Oil and Natural Gas Commission, Government of India. And after having a very long innings there, he has started his career as a researcher in University of Calcutta and going to have his PhD, I think by a couple of months. He has worked in ONGC for more than 34 years. His experience includes commissioning, modifications, safety, operations, artificial lifts, pressure maintenance, enhanced oil recovery, and planning in offshore and onshore oil fields. He has also vast experience in marketing of upstream and downstream petroleum products. He has attended several training programs in USA, Canada, and Singapore. He has undertaken the Advanced Management Training course in Indian Institute of Management, Calcutta, along with its integrated industry visits in Belgium, Netherlands, France, and Norway. He has published technical papers in Chemical Weekly. He is graduated as BSc Chemistry and BTech Chemical Engineering from University of Calcutta. He is an MTech in Chemical Engineering from Indian Institute of Technology, Kharagpur, and has also acquired MBA degree in finance from IGNOU, New Delhi. He is the lifetime professional member of Indian Chemical Society and Indian Science Congress. He is now doing research in University of Calcutta. He has been recognized with the Best Researcher Award 2020 by VD Good International Professional Association. He has participated in many international conferences across the globe, namely Abu Dhabi, Amsterdam, Bahrain, Bangkok, Barcelona, Cape Town, Dubai, India, Jakarta, Kuala Lumpur, London, Paris, Perth, Shanghai, Shenzhen, Singapore, Telangana, Yangon as invited speaker. So his today's topic, this is very, very important towards our goal, that is the sustainable development for Indian industries. The topic is prospects of coal-bed methane, that is CBM, coal-bed methane. And already you were aware that there is one such company in known as the Matix Fertilizer near Ondal in our state. So he will discuss the prospects of this particular gas, fuel gas, that is coal-bed methane. Over to Mr. Mondal for his excellent presentation. Sir, please.
Thank you, Dr. Swami Vedagananda ji, for introducing me. Of course, I have met many of the participants earlier also during this internship course. I think I had already spoken on 6 different subjects, but as you have already mentioned, sir, this is very pertinent in view of the sustainability of energy sector, because we are aware of many changes coming in the energy sector because of definitely the environmental point of view. So this particular energy source, that is what I am going to discuss today, is coal-bed methane. Also similar to that, because it only contains natural gas. It does not contain any oil as such, and it does not contain even coal also. Although it will be taken from the coal bed, but still this gas does not have any coal when we will utilize it. So the chances of pollution will get reduced tremendously as we are progressing towards renewable sources like solar, and tidal, wind, and all those things. But I don't think we can totally forget the carbon-based energy source also, because other than the production of energy, the carbon is required for petrochemical industry, for fertilizer, and many other prospective chemicals. So the energy requirement as well as a source of carbon from coal bed methane will have a very important usage that we are trying to understand through this particular topic uh, in this presentation. So what I'll do, I'll first introduce about coal bed methane, what exactly it is. As the name stands for it, almost totally to understand. Even then, we'll just have a few more description about this particular gas, that is coal bed methane gas, and history of CBM, that is history of coal bed methane, how it has come up and since when, origin of CBM, where it exactly found, and how it has been generated, how many years it took, or what exactly was the source to get CBM to get generated in that location. And of course, before we go for extractions, this is our procedure. We'll have to find out where exactly the CBM locates so that we can go for commercial production from that location. And the production system, this is very important. We have already discussed about how this crude oil and natural gas have been produced from underground, but although this is also underground gas, so whether the production system will be similar or something different is there, that we'll discuss in this particular sector. And as we are aware that from any particular field, whenever we'll go on taking the production yields will go down with time. So in that case, how to enhance the production from that location, that also we'll discuss. And we'll have another aspect, because as we have been habituated with the natural gas for so many years. So what exactly is the difference between natural gas and this coal bed methane? That also will take up. And what are the uses of coal bed methane? We'll again explain. Global scenario as well as Indian scenario. So all these things we'll cover in our presentation. So first, if we have to introduce, we must tell you that CBM, that is coal bed methane, it's a natural gas that occurs within the coal deposits. In case of natural gas, what we have found that is available not in the coal deposit, but in the underground sandstone or limestone structure or sediments. But here it will be in the coal deposits. It will contain mainly methane gas. And methane, of course, is the principal component for natural gas also. But in case of natural gas, we find other than methane like ethane, propane, butane. But in case of CBM, we will mainly find that it contains methane. Even more than 96%, 97% methane is available in CBM. CBM is usually a sweet gas because it typically contains very few quantum of sour impurities, that is hydrogen sulfide, nitrogen, or carbon dioxide. These constituents or components are also available in many of the natural gas sources. That's why we have discussed about sour gas and sweet gas in terms of H2S ppm. But in case of CBM, we will find that it is mostly sweet gas because the HPS ppm is very, very less. CBM is generally near pipeline quality gas. Means when we will produce, we find that this gas is more or less compatible for commercial use. It does not need much processing requirement from the gas point of view. Of course, from the water point of view, there will be a requirement for processing. But as such, from the gas quality point of view, this is very much compatible for commercial use. And CBM is typically produced at lower pressures. In case of conventional natural gas, what we find in sandstone or limestone structure, which is more or less 500 to 5,000 meter depth. But in case of CBM, it is not at that depth. It is hardly 1,000 within 1,500 meter depth, and it is its pressure is very low because basically it is at hydrostatic pressure when it is generated there, and it remains at that pressure only and get under pressure with water. That's why when we release the water, it comes at very low pressure. And when burned, CBM generates as much heat at petroleum-based natural gas. So that means from the British thermal unit point of view, that is BTU point of view or the calorific value point of view, the CBM is as good as the petroleum natural gas. Now, if we are to talk about its background, what we find that it is not a very old phenomenon because coal, in fact, we have started mining for more than 160 years before. But this particular scenario came for coal-bed methane, whether it can be a source for natural gas or not. That came only in 1970 when there was energy crisis because a lot of industrialization were taking place across the globe, and whatever conventional source of energy was there, like coal, crude oil, and natural gas, they were more or less limited. So there was a requirement for looking for more and more energy sources, and in that way, this particular scenario had come in 1970s onwards, and subsequent to that research for getting the origin of coal-bed methane, the scientists had tried basically how it has been accumulated there, what are the distribution among the coal deposits, and what are the availability and recoverability. These are very important for commercial requirement. So that's why those things also have been studied during this period. And finally, in the early 1980s, a new industry was born when mining company started capturing and selling the coal-bed methane. So it is just 40 years old idea to take coal-bed methane as a commercial product, as an alternative natural gas. Coal was mined more than 160 years, as I said, but this commercial use of coal-bed methane has come only after 1980. Coal-bed methane, which was treated as a mining hazard and being ventilated from mines to remove the gas and release it into the atmosphere before mining, had become considered as a conventional gas resource. Actually, before this coal-bed methane was produced commercially for making it an alternate source of energy, before that also it was present in the coal seam or coal bed, but it was not known how it is to be produced and whether it is required to be produced. So it was basically mining hazard, because that if that gas is there, that is definitely a problem for people to work there. So it was ventilated from the mines. So in that way, it came into the atmosphere, that gas, without having any use, and coal was being mined. So this was the procedure. If we would like to see this aspect through this diagram, we can find that in the past, that is before 1980, this coal-bed methane was known as a disaster gas because it was not known that it can be really used as a natural gas resource or not. And for coal mining safety, it has been vented. But after 1980 onwards, when this particular gas has been identified as an important source of energy, then it has got two important aspects. One is that coal, which releases a lot of CO2, that quantum also will go down, because a lot of energy can be converted from coal bed methane from coal. So this is basically will help the environment to reduce the greenhouse gas. Not only that, when this methane gas will come to the atmosphere without burning, then also it will be treated as a greenhouse gas. So that component will go down in case we can start taking the production of CBM. And of course, it is a clean energy, because all natural gas, wherever the carbon is less and hydrogen is more, we can understand that that will give more and more heat value, at the same time less and less pollution, because CO and CO2 will go down. So this is the present scenario, and this in this way we are now considering that CBM is a resource exploitation and greenhouse gas mitigation. Now, if you have to understand about the origin, it comes like the crude oil and natural gas, which comes from the plants, trees, sea animals, and all those things over a million of years. More or less in the same fashion, the plant material such as roots, bark, wood are also deposited in swamps or swampy lakes, and they undergo bacterial and chemical changes over a period. And in that way, the peat deposits first started coming or generated. This is the peat which has come from the plants, trees, and woods. And as the peat is buried deeper under layers of sand and mud over millions of years, it changes to brown coal. This is a brown coal, and then bituminous coal, and finally anthracite coal. These are also known as coalification process. How this coal is getting matured in the earth. That is also we are aware that it has got 4 phases from peat, lignite, bituminous coal, and anthracite. This is first generated before coal bed methane. After that, as the coal is formed, the decomposing organic material produces methane gas, as well as nitrogen, carbon dioxide, and other gases. So when these things have been generated, and there is a lot of pressure from sands, surrounding sands, as well as temperature, so the gas will start evolving, and that gas will be known as coal bed methane. So CBM is generated by the same geological process known as qualification process that turns plant materials into coal. So the process which is used, or which is practically seen for coal generation, the same process practically necessitates for making the coal bed methane also. And the burial process puts pressure on the coal, which keeps much of the gas absorbed in the coal. Now, where that gas will go? That gas will remain there, and it will be absorbed by coal only, because here there is no source of any sandstone, limestone, sand, or clay. All the things have been converted to coal only. So the gas which will be evolved from this coal bed basically will get absorbed in the coal itself. So that's why, from this generation point of view, we'll find that some definitions are very important to know while we will be discussing about origin of CBM. Number one is coal seam. The coal seam is a dark brown or black banded deposit of coal that is visible within layers of rock. These seams are located underground and can be mined using either deeper mining or strip mining techniques, depending on their proximity to the surface. So here from this picture, you can find that how coal has been generated over a million of years time from the plants, and that will remain there. And this particular spread of coal will be known as coal seam. And when natural gas is obtained from coal seam, it is known as either coal seam gas or coal bed methane. So the gas which is generated here and trapped inside the coal spore, that will be known as coal bed methane. Another term is very important, that is called coal partings. When we are finding the coal seam, we'll find that there are certain layers which does not have any coal. See, these are the layers which does not have any coal. So what has happened basically, that when such deposition of plants and trees and woods are there in the swampy lakes and remain there, coal has been formed. But when the floods and all those things are natural calamities are happening, then a part of that deposit will flow away. So these are the path basically. This path, the coal which was there, that will not be remaining there. That will swept and that will move away. So when those parts are getting generated in the coal seam, that will be known as parting. So coal parting is nothing but the layer which does not have coal, because the coal materials have been swept through the floods. Another is coal cleats. This is another definition which is required to know about the origin of coal or origin of coal bed methane. This is how this coal is getting generated, whether it is face-to-face generation or it is perpendicular generation. Means like welding, we know that lap welding and butt welding. So if it is face-to-face, so that means if we are finding that this coal field is expanding towards its face only, towards the parallel to where it is generated, then it will be known as face clip. And when it will be perpendicular to that, means this way, then it will be known as butt clip. So this is basically when the coal field is getting expanded, we should know basically this idea in the beforehand, so that we can estimate how our wells will be located in the coal seam to take maximum production from the coal bed methane. So that's why this formation of coal cleat, whether it is face cleat or butt cleat, is very important to know before we go for coal bed methane. Now, when this coal bed methane will be formed, as we have discussed about origin, from where it will be originated, now it will be generated either through chemical reaction or bacterial action. So there will be a chemical reaction, means over time, when heat and pressures are being developed over that coal field, then there will be a chance of certain chemical action which will generate methane gas. So this is known as thermogenic production. And the gas in higher rank coals is a result of thermogenic production. Means as we know that pit to lignite to bituminous to anthracite, that conversion is taking with the time only. So more and more time is being given to that coal field to get matured, or that means more and more methane gas will get generated through chemical action. And bacteria that obtain nutrition from coal produce methane as a byproduct. Means the methane gas will get generated from this rotten coal or whatever wastes are there inside the coal or alongside the coal, that will get with certain bacterial action, and which will be known as biogenic production. So these are the two procedures or reactions and actions happening in the coal field, so that coal gets converted to CBM over time. Now, how it existed, how it exists basically within this coal. See, coal is basically a very porous material. It has got a lot of surface area inside as well as outside. So as this solid and coal bed methane gas, so gas will get absorbed within this solid surface inside as well as outside. So that's why we'll find that a lot of gas which has got generated in the coal field ultimately is getting absorbed by this coal itself. And that CBM exists in coal in three basic states as free gas. It will remain as free gas also. It is otherwise gas dissolved in water in coal. So every coal field has got a lot of water also. So it can be absorbed by the water in the coal field, as well as it is also absorbed on the solid surface. So this coal bed methane which is getting generated in the coal field or coal seam will be available or remain there in these three basic states. Now with quality, coal quality, if we are to talk about CBM quantum, you see as coal mature from pit to anthracite, the associated fluids transform CBM. This has already been explained that with qualification, when we are going from this phase change, pit to anthracite for coal, how this more and more CBM gas is getting generated, initially through bacterial action or biogenic and then thermogenic. The low rank pit and lignite have high porosity, high water content, and produce low temperature biogenic methane. So biogenic methane is basically mostly available for peat and lignite coal fields. And as coal fields mature into bituminous type, water is expelled, porosity decreases, and biogenic methane formation also decreases because temperature rise above the most favorable range of bacteria. You know, for any bacteria, it needs certain temperature to survive. If the temperature of that location increases, then bacteria cannot survive. So when this coal is changing the phase from lignite to bituminous, the temperature is likely to be increased further and water will get reduced and bacteria also will not survive. So the chemical reaction starts taking place. And as anthracite is getting formed later on or finally, then less methane is generated and little porosity or water remains in the matrix. So only the chemical reacted methane will be available in case of anthracite. So that's why the quantum will be reduced as far as the generation of CBM is concerned. And when the desorption will taking place, means when the coal bed methane will be taken for production, definitely now the desorptions will be helping to release more and more gas. So what we'll find that natural desorption occurs when the fracture system releases water, the adsorb, just 1 minute. Okay, this natural desorption occurs when the fracture system releases water, the adsorptive capacity of the coal is exceeded, pressure falls, and the gas trapped in the coal matrix begins to dissolve and move to the empty spaces in the fracture system. Basically, whatever way the adsorption has taken place, just the reverse way, we'll find that desorption is taking place when the coal bed methane will start producing. And the volume of gas typically increases with the coal rank, whatever is the coal bed depth and the reservoir pressure. So this is, you can see how the porosity have been changed from peat to anthracite, and therefore how much coal bed methane will remain there in the pores. Now, if you have to find a CBM location, there are many procedures. We have discussed some of the procedures for even finding this oil field also. Similarly, for CBM gas field also, more or less similar studies are there with certain changes, of course. First one is electrical survey. The purpose of DC current electrical survey is to determine the subsurface resistivity distribution by making measurements on the ground surface. Practically, when we see the subsurface containing many different items, the resistivity changes. And we can put the electrode on the surface or even up to a certain depth also and take the measurement to this parameter, that electrical resistivity. And then we can understand whether this structure has got certain deformity or not. And from that, the geologists can understand whether CBM is likely to be available in that coal structure or not. Then electromagnetic, earlier it was electrical resistivity, now we will go for electromagnetic waves. So this is also more or less similar phenomenon, only in this case we will measure this electromagnetic property. Instead of DC resistivity, where the electrodes are there, we will have a different transmitter and receiver, that surface receiver, to measure the electromagnetic waves. So that also will give some idea whether that subsurface has got certain deformity or not. We can go for magnetic properties also. That coal has a low magnetic susceptibility when compared to most other rocks. So if we measure the magnetic properties and if we find that the magnetic property has gone down in a particular location, we can understand that the coal is likely to be generated there. And if it is in the fault, mostly it looks to be made available in the faults only. So the geologists, when they go for analysis of the fault generation in the earth, they can really correlate that this magnetic property and fault combiningly can dictate whether coal field and coal bed methane will be there. Another is called ground penetrating radar. This is basically the radio waves which are again generated from the top, and if when whatever path will be there, in that path if any obstruction comes, that will be gets recognized. The way basically we use the radio waves or the radar for finding any source of any flying objects or whatever. Even a trapped person in the tunnel also can be located through this radar system. So that similar way, the radar can help to find out whether the coal field is there and how much coal bed methane is likely to be there. And finally, the seismic method. This is the most scientific and common method, and this is the most prominent decision-making method, we can say. That is to create the sound and take the echo. And if the sounds are reflected and getting basically disturbed by different layers, that will help us to understand what sort of structures are there under the earth, and in that we can correlate whether coal bed is there or not. Then after we understand that coal field is there by all these 5 tests, or especially for seismic survey, then we will have to estimate how much coal bed methane is available in that coal seam. Because here we are not in a position to extract the coal before that coal bed methane is generated. So we will have to estimate there itself. So for that, what we will do, we will extract a core from the coal seam. This is very important. We'll do a drilling the way the oil field also is being drilled for crude oil and natural gas. In the same fashion, here also we'll have to drill, and we'll have to go up to that coal seam and take a sample of core. And that core will ultimately will be studied basically in different way. First of all, its porosity will be measured, permeability will be measured, and its water saturation will be measured, and in that water how much coal bed methane can be there. All those things can be estimated by taking that core sample. And after that core sample is taken and coal bed methane quantum is estimated, these are all preliminary steps before the production starts. So wherever we will find a coal bed, we will have to first go for all these steps before going for any production well. So after completing those things, then the first step is CBM production is to drill and complete CBM wells. CBM wells are completed in several ways depending upon the type of coal in the basin and fluid content. All coal will not have the same quantum of bituminous, anthracite, lignite, peat, and all those things. So we'll have to first study from that core which sort of coal field it is, because the water quantum as well as the as we said that thermogenic and this bacterial reactions will be there to form the coal bed methane. So for estimating and understanding that coal bed methane is now possible to be produced. So based on that only these production steps are being taken. And sub-bituminous coals are softer and less competent than the higher rank low volatile bituminous coals, and therefore are typically completed and produced using more conventional vertical oil bores. Basically, this is talking about that casing phenomenon. Means although we'll be saying that in case of coal bed, depth is quite less compared to the oil field. So many layers of casings will not be required here. Even then, it is very important to know what sort of depth is there in any particular coal bed, and accordingly we will have to go for designing that production steps. And final step, of course, CBM production is to streamline the well completion. Now, what are the informations basically required then for this completion of the CBM well? Number one is the reservoir depth. Number two is the drilling histories. Suppose if some wells are already there, that will help to go for expansion of more and more wells. So the drilling history also will help to go for another wells to be drilled. Environmental condition. This is again very important. If the coal fields are very close to cities or very close to some populated area, definitely the impact on the environment is very big in that case. So this is also very important for going for CBM well completion. And there are many other informations which are also important. That is the published literature, means the technology, field study, the operators who will be, whether it is required to be hired or not, service companies and regulatory agencies. So these are the informations very much required for starting this CBM well completion. And we find that CBM wells are usually less than 3000 meter. As we say that in case of oil field, we can go even up to 5000 meter. But here, basically, the depth is quite less compared to that. So that's why the well cost is quite low compared to an oil field well cost. Several rig types and sizes are suitable for this. The most common rig is the conventional rotary drilling and otherwise water well rigs. The rig which is utilized even for groundwater borewell also. The same rig also can be utilized for this in case the depth is low. So this is the picture what we can explain. This is a conventional rotating drilling rig. In case you have to go up to 3000 meter, this can help us to go for casing as well as production tubing. And whereas this is a rig which is very easy to take to different locations, but it has got very limited horsepower, so it does not go more than 1000 meter or 1500 meter also. Then if we see the underground structure, you see these are the underground structure. Here it is a caged hole, it is a bared hole. So what it is saying basically that CBM completions have been developed to link wellbore into coal seams. The most completion type is to run casing, perforate and hydraulically fracture the coal seams. So this is more common. Means we will have to go for casing. This is the tubing, and there will go for perforation, and we have to hydraulically fracture also. If we find that the permeability means the channeling between the coal pores are very less, then we may have to go for hydraulic fracture also to open up those pores by increasing the permeability. So this is most common. And in case we find that the structure is already fractured and it does not need much exercise to be done at the bottom, then you can go for, you can say here, it is written that open hole completion may be sufficient. So this is open hole. So we'll lower the tubing with the perforation in beforehand itself. And then what we'll do, finally we'll utilize, here you can see, we'll utilize some pump, because all coal bed methane gas are available in the coal bed along with a lot of water. Basically, as we said, that the water which is there in the coal bed, that only contain the coal bed methane gas in absorbed condition. So that water is to be removed. And secondly, this field pressure is also hydrostatic pressure. So if the pressure is to be reduced, then also we'll have to reduce this hydrostatic head. So we'll have to take more and more water from there. So this way we can go for CBM gas production. So CBM well construction is different than oil field oil well or gas field gas well. Here we will find that in the casing there will be two sources of taking production. The inside one will be water, and that will be connected with either progressive cavity pump, that is PCP, or centrifugal pump, submersible pump, and that will continuously take water to the surface from the bottom from the coal field. And then the gas which will be evolved because of reduction of this hydrostatic head, that will come to this casing or this annulus, and that will be produced from the top. Here the Christmas tree will be there for controlling the gas. Here the Christmas tree will be there for controlling the water. So this is a typical, you can say, completion of CBM well. You see, this is the water side, this is the gas side. This is how the gas has come. This is how the water has been taken. And this is the submersible pump, which has been used basically to take this water source from this field to the surface. This is another picture. I mean, in the surface, you can find little different way to look into, but all are principally they are all similar. That we'll have to take water from the inside tubing and gas from the annulus side only. Now, in the surface, after that gas is collected from that Christmas tree, which is having for gas controlling, so that will have a lot of vessels to separate out the gas from the water. This does not have much water because the water got a separate stream altogether. So we will have basically two different way of handling. One is for produced water, another is for coal fines, third one is for low pressure gas. So here we can find the gas along with some quantum of water and some quantum of coal fines also. So this sort of separation, that is separator and flow lines and transfer pumps and storage facilities will be required. Storage facilities is basically not very common because as we know that we will not be going for LNG storage for such small quantity. Of course, in Australia, Queensland, they have got even LNG storage facility from this coal field itself. But in India, we do not have that much quantum of commercial gas resource for coal bed methane. So we will not have a storage facility. We will directly go for a pipeline to take it to consumer locations. And the gas distribution, that means we will have dry or wet gas. Of course, dry gas will be utilized for most of the consumers, and they need certain pressure requirement also. That pressure can be made available to them by themselves, or the producers will have to pressurize it and give it to them. And the purity, of course, will be required based on where it is utilized. And finally, there will be a measurement facility to make the billing and payment and all those things. So what are the surface facility? If we are to describe again, we find that separators can remove most of the produced water from the flow stream, but heated separators or dehydration units are needed to extract the remaining water. Filters may be required to remove coal fines produced with the water to keep valves and equipment functioning properly. If scale forming minerals are present in the water, chemical treatment may be needed to protect steel tubulars and surface equipment. So there is a possibility in case of oil also we find that scaling may happen because of strontium or calcium carbonate deposition. So in case those things also are found in some coal field, we'll have to go for chemical treatment. We will have to utilize scale inhibitor so that the scaling will get reduced. And if the water is to be disposed of offsite, trucks or additional pipelines will be required for water transport. Usually pipelines are laid to take this water to a distant locations for processing and supply, because it is having a lot of contaminant, so that needs to be separated out, otherwise it will spoil the environment. So that processing has to be taken place for this water. And we can go for water disposed oil also. In case we find that this water cannot be utilized or the quality is really bad, cannot be reused for any purpose, then we can dispose through water injection wells. So this is the surface facility for water. You see, these are the surface facility. See, it can be utilized for municipal use if proper processing is taking place. Otherwise, it has to be discharged and put into the some water stream. It can be put into the water stream under the earth also. It can be taken for hydraulic fracturing, as we said that the water is required for fracturing in the coal bed also to create permeability. We can utilize same water for this purpose also. A lot of industrial use and irrigation use also can be made available through this CBM water. And this is a typical CBM gas facility where H2H, in case it is there, then that can be removed through amine scrubbing or molecular sieve, or dehydration also is taken place through adsorption of moisture. So all this basically gas processing is similar to the way we process for natural gas. Nothing new in that. Technology is similar. We can utilize molecular sieve or amine scrubbing and the glycol dehydration. Everything is similar. And in case we have to go for LNG, then we'll have to go for cryogenic processing. So after final dehydration, we'll have to go for metering for this gas. And this is the typical well side view. This is where the CBM well is there. This side is water and this side is gas. This is the gas processing, and this is the water which is gathered in a single location in case it is to be treated for its further use either for irrigation or for some other purposes. What are the factors that means being considered for CBM gas production? Several factors. One is the fracture permeability, because if the permeability is less, then you have to go for hydrofracturing. So this is important. Second thing, the procedure which will be developed for gas processing, whether that is possible in that particular location or not. The coal maturation, that means whether it is anthracite bed or bituminous, that is also very important. The coal distribution, as we said, that face clit or butt clit, that distribution has to be known so that we can go on adding the wells in that particular location. The geological structure and completion styles, all these things are very much important. And finally, of course, we will have to know the hydrostatic pressure in that particular water depth, so that water will be released and that gas can be taken for production. So these are the basic factors. There are other factors also, as far as the gas component is concerned, whether it contains only methane or it has got other gas also, that can be established, and economically it has to be determined whether that gas will be utilized for commercial production or not. As long as the pressure exerted by the water table is greater than that of coal, the methane remains trapped in the coal bed matrix. So as we have already clarified, that unless we remove this water from the coal bed, the coal bed methane cannot be coming out from that well. So every coal bed methane had got the procedure to release the hydrostatic pressure first by taking the water through the centrifugal pump. And then if we find that the coal bed methane gas quantum has gone down over a period of long production time, then we can go for addition of production from that mature coal bed or coal bed methane field. The way we had basically discussed about the enhanced oil recovery, the similar procedures are utilized for CBM enhancement technique also. That means we can utilize injection gas, either CO2 or N2. We can go for thermal also. We can go for microbial also. So these are the procedures basically we need to discuss again, because we are already clarified for enhanced oil recovery in crude oil production enhancement system. So the same technique is being utilized. Here you see that this is the coal seam, this is the surface, this is the subsurface, and in that what we have utilized the microbial, because we have already clarified that coal gradually generates coal bed methane through bacterial reaction. So if we put certain nutrient, that action can be made faster and we can get more and more coal bed methane from that location. This is for CO2 injection. So now, as we have also understood about CO2 sequestration and all those things, so wherever we will find CO2 or even air or nitrogen, we can inject that. Of course, oxygen should not be injected in this particular case. In case we have to think only for gas phase, but in case we have to go for thermal, we can increase the temperature also. There we can utilize the oxygen or the air also, and then that partially burn some of the coal and will, or even the coal bed methane gas, and then the pressure will get increased and more conversion from coal to coal bed methane can be generated. So these are the three important techniques for increasing the coal bed methane gas production. And so what are basically in the surface facility we find, which can be given either on contract to some operator, or can be operated by the company themselves. The first one is well site facilities, which will have office, drilling rig foundation, cellar pit, basically where the Christmas tree is being located and well bore is drilled. That rig equipment, evaporation pit for evaporating the produced water in case it is less in quantum and cannot be utilized for any irrigation purpose, then we can utilize them through evaporation pit also. Chemical handling for, as we said, for this scaling and all those things, or even for dehydration, diesel storage tank for power generation and fencing. So these are the facilities can be given for maintenance contract also. The GGS facility will have separator, surge vessel, dehydration and pumps. Pump normally screw pump and reciprocating compressors are utilized, and the water treatment plant and flare system, they also can be given on contract. Instrument system and SCADA also. Power generation network, in case direct grid power is not there, we can generate power from the part of this coal bed itself, coal bed methane or coal, and we can go for fire and gas detection system. Then this is another thing which we have, I think, heard just 2 days before also, that coal, underground coal gasification. Practically, they had talked about the coal gasification in the plant, not in the underground. Only it is talking about how the coal can be converted to syngas by partially combustion through either help of catalyst or without catalyst. So the same procedure can be utilized underground also. And if we do that scenario being developed in underground, that will be known as underground coal gasification. And in that, what is required then? One well is required for injecting air or oxygen to burn partially, and the other well will be taken for the syngas, or the coal bed methane gas will be converted to syngas, which will now have carbon monoxide, hydrogen, and carbon dioxide. So when we will utilize this, we will have to utilize some water also. In case this water is not sufficient for making hydrogen, then we can go for underground coal gasification along with some quantum of water also. What are the impacts? Basically, it has got a lot of advantages over the coal, we can say. Number one, the coal productivity can be increased through coal bed methane, because earlier this gas was being ventilated without using, so that can be utilized. And it is a domestic source now to reduce the import. And of course, it is a clean burning because of only methane gas. But it has got main disadvantage to the water handling. And of course, the land degradation may take place where the coal field is there, and water contamination and pollution also can take place. So these are the disadvantages. Otherwise, a lot of advantages are there. But this water can be otherwise utilized as a good source of prized source, we can say, of fresh water in many arid regions. In case of desert in Rajasthan and all those things, but there is no water at all. So there, this water can be utilized after some treatment, and it can be considered as a important source of water. Now, if you are to compare with CBM gas with natural gas, this comparison is very simple. That CBM contains only methane, whereas natural gas contains methane as well as higher hydrocarbons like ethane, propane, and butane. Conventional natural gas is formed in limestone and shale formation, and pressure and temperature unite to transfer organic matter into hydrocarbons over time, similar to thermogenic production in deeper coal. So here you can say it is produced in limestone and shale structure, whereas it is, in case of CBM, it is in coal. Natural gas migrates upward until trapped by geologic barrier or fault. In this case also, it is normally generated in case of fault only. The depth is, in case of conventional gas well, 4,000 to 12,000 feet, whereas for CBM it is quite less, up to 5,000 feet. And CBM can be used in very much the same way as conventional gas. But only thing is, if we go for their production criteria or production scenario, then we find that in case of natural gas or the conventional natural gas, the gas production initially is very high because of a lot of pressure in the reservoir, and then the pressure will go down and the gas production will go down. And if we see the water quantum during that period, initially the water will be less and gradually it will be more. But in case of CBM, you will find that the gas quantum initially will be less and then it will be increased. This increase is because of this water hydrostatic head is being reduced. And after that, when the coal bed methane resource will go down, then the gas quantum also will go down, as well as the water also will go down. In this particular scenario, we'll have to go for enhancement of the gas production through the technique what we have already discussed. It is known as unconventional gas. This is the coal. You see, this is unconventional. This is the unconventional like shale and this tight gas, and this is the conventional non-associated gas or free gas along with the oil or oil field. So this is this particular gas which was along with the crude oil field or even the natural gas field. It was only known as conventional. Any gas resource which have come after this conventional procedure are known as the unconventional gas. What are the uses? Coal bed methane is a cleaning burning energy source, a clean burning energy source. It is suited as a fuel for production of electricity, for production of fertilizer, plastics, residential and commercial heating, and as a vehicle fuel also. So there is a plan, for example, that SR is taking CVM production from Raningaj area and bringing it to Kolkata in terms of CNG and to be utilized for vehicle only. So these are the usage. And if we are to see what is the maximum use globally, maximum it is 31% for power generation, but 39% for industrial. As it has got a lot of carbon resource, it can be utilized for fertilizer and plastic also. That's why so much use is there globally for CBM. And if we are to go for global scenario, you see it is not very common across the globe. Only few locations have started taking the coal bed methane production. This is Canada, this is North America, and this is Russia, and this is some quantum in the Asia Pacific region, and this is Australia, and some of course resources coming in India also. And if we find their percentage, you will find that only 6% is being globally utilized from the total natural gas resource from CBM. In case of India, CBM prospect, India had formulated CBM policy in 1997. So although from 1980 onwards, we found that global development is there, but in India, this policy has been generated in 1997 to go for commercial production from CBM. Before that, two blocks were given on nomination basis to ONGC, but actual commercial scenario has come up after 1997. And highlight of this policy that the blocks which are having coal bed methane in the coal field, they are to be awarded through open international competitive bidding. So auction will take place time to time so that they can be allotted to the bidders who are interested to take this coal bed methane gas for commercial production. No participating interest from the government will be there in that bidding scenario. No upfront payment also is required, no signature bonus. Exemption from payment of custom duty on imports of required for CBM operations. So whatever equipments, whatever materials will be required for CBM production, custom duty will not be required. So this is an incentive given by this policy or through this policy. Freedom to sell gas in domestic market. Now the producers can sell this gas by themselves. It's not required to be sold through GAIL or gas authority or through the government's directive. The freedom is there for the developing the domestic market. It cannot be basically taken for export, but in the domestic market, it can be decided by the producer itself. Then 7-year tax holiday. So first 7 years, as this lot of investments will be required for developing this new area. So first 7 years, there won't be any tax payment related to this revenue generation, and 10% royalty payable to state government. So it is lesser than the crude oil royalty, which is 12.5%. So these are the benefits being decided for CBM policy. And so far, 4 bid have already been completed. One is 2001, 5 blocks are awarded, ONGC, SR and Reliance. 2003, 9 blocks, ONGC and Reliance. 2006, 10 blocks, BP, Arrow, Geopetrol, Coal Gas. Some private companies have started joining other than this major like SR Reliance. And 2009, 7 blocks, SR, Data Energy, Tata Power, even Oil India Limited, and Great Eastern Energy Corporation. So these are the companies which have been taking the coal blocks, 31 blocks, and 2 blocks are already given before auctioning. So total 33 blocks have been distributed, and total resources around 91.8 TCF. And but the established GIP means which can be taken for commercial production is 9.9 TCF. This is still, we can say, huge quantum. And first CBM wells were produced or came up by ONGC as per that policy. from 97 to 99, 4 wells at Jharia. And these are the blocks which are spread along with the India, mostly in eastern part. Here you can see West Bengal, and uh, I have got details also of that field. Jharkhand, Rajasthan, Gujarat, Odisha, Chhattisgarh, Madhya Pradesh, West Bengal, Tamil Nadu, Telangana, and Andhra Pradesh, Maharashtra, and Northeast. These are the locations where CBM fields are there, and their quantums also have been specified. And the total area is almost 52,000 square kilometers. It's a huge area, and this total whole area is known as Gondwana Basin. So this is the basin where all these fields are located in eastern sector of coal bed methane. And commercial production, as we say, it has been started in 2007. Although these wells have been started in this period, but you can say the commercial production has started only from 2007, because we had to find out the gas consumers also in that location. So in that way, the CBM has been produced from 4 blocks by this time. Jharia block in Jharkhand by ONGC, Raniganj East in West Bengal by SR Oil, Raniganj South in West Bengal by Great Eastern Energy Corporation, and Sohagpur West in Madhya Pradesh by Reliance. These are the 4 major locations, and domestic production of CBM is likely around 2 million meter cube per day in the current scenario. And these are all the facilities which have been earmarked, basically how this GGS, GCS, and EPS will be built up in the site locations, and how many wells will be drilled. So total 366 development wells are being drilled to get the production of 2 mm SCMD. So the potential of each CBM well is quite less compared to the natural gas well. If we compare with the quantum of gas being produced from each well, we'll find that CBM well produces lesser quantity of gas compared to natural gas. And this is in details for SR CBM project. We will not be discussing details. This is their surface location. It is mostly in West Bengal, where they have started the commercial production. They have also got the field in Jharkhand, Chhattisgarh, and Madhya Pradesh and Odisha also. And this is the Reliance. They have started working in Madhya Pradesh from 2017. They are yet to take commercial production from West Bengal as such. And this is GECL, that is Great Eastern Energy Corporation. They have also started in Raniganj. This is their field location. And they have already laid a pipeline of 77.62 kilometer. And this gas also has got a very bright future as per estimation given by GECL. And this particular gas, SR gas, this was utilized for Matrix fertilizer plant, which has been developed near Ondal. But as the gas production went down very quickly, maybe in 3-4 months time, so this fertilizer plant was remained idle for last 3 years, and now they have started production from this month after getting the GAIL gas from Uttar Pradesh, Gujarat and through Uttar Pradesh. So finally, if we have to conclude that coal bed methane production is a rapidly growing industry that will undoubtedly continue to expand under the global demand for alternative energy sources. India is the 5th largest in coal reserves, not in coal bed, and 3rd largest coal producer at this moment. Water depletion from coal bed methane production can adversely impact adjacent residents, farmers, business that rely on local groundwater and surface water. This is a gray area. This is to be sorted very quickly and efficiently. Otherwise, that field cannot be developed. And finally, when the use of cleaner energy sources must be encouraged, such development should not proceed to the detriment of local communities. So the local inhabitants should be protected from coal bed methane's exploitation in that coal field area. This is all about coal bed methane. I have tried to finish in quick time because it is a huge description. Actually, I had only highlighted to make you understand that what is coal bed methane, how it has been generated, how it has been produced or being produced, who are the companies engaged in India, and what are the possible locations in West Bengal which will definitely get benefited out of this CBM development. That's all. Thank you, sir. Thank you all.
Thank you, our Mr. Ashwinendu Mundal, our Ashwinendu, this is a very, very important and also innovative piece of information. I hope the participants got very much benefited. I request the participants, if any questions arise, so you can clear the doubts. Our next speaker, Mr. Vishwajit Shon, already, this is his second day lecture. He is Assistant Vice President, Reliance Industries Limited. So he is also he has also joined. So on this backdrop, if the participants are having any questions, you can free to ask. Otherwise, we can start the next session with a generous thanks to our Ashwinendu.
Thank you. I think there is no question I can see.
Today, the Jalapur group has not joined, it seems.
I see.
Actually, they are having some class test examination.
Oh.
That is going on. So that's why I see the occasional comments in the WhatsApp group that
but
we are
students from Heritage also are there, no?
Yes, these are mostly heritage. Mostly they are heritage students. Those are
We have heard many questions from Sayan Mukherjee. I don't know which Sayan Mukherjee. There are two actually. One is present today. This is which Sayan Mukherjee? Can you respond? Sayan Mukherjee. Sayan, can you?
Sayan, please. I mean,
can you tell from where you are? Durgapur or
Heritage? No, one is.
No, sir. Actually, I have done MTech from Heritage.
Okay.
I have a MTech in renewable resources.
Okay. So you have already.
He had BTech from Heritage and then also MTech from Heritage. Yes.
So whether you are aware of coal bed methane and.
Sir, from your lecture only, I come to know a great deal about coal bed methane. But before that, I heard about that. I have heard about that. I have not gone through in detail, but I was familiar with that.
Okay. You have heard the name of CBM and coal bed methane, but practically how it has been being produced or how it has been generated there, where exactly it can be located, those things are not known in detail.
No.
Right?
Yes, sir.
I think then this session must have given some idea by this time that you could know something. Is not it?
Yes, sir. Yes, sir. Your slides are very much helpful.
Okay, I had to finish very quickly also because this is a huge exercise, coal bed methane. It cannot come up in a single day. It is a total energy resource basically. So if you have to cover all the angles, so definitely it takes.
Yes, sir.
Any other question from any other? Tasi?
She has not joined, it seems.
No, Tasi is there. Tasi is there. Yeah.
Oh, I see.
Tasi is from Ladakh. That day we could introduce. Tasi, are you there?
Yes, sir. No question, sir.
No question. That is fine. But how are you right now?
Yes, sir.
Okay. What is the temperature now at your place?
It's varying, sir. We have a different temperature, so it's depend upon. So in day in midday it is about 20, and it's evening or late night it's about 2 to 3 degrees.
Oh, so you are to feel cold also in the night. Huh?
Okay, thank you very much.
Thank you, sir. Thank you, sir.
Our next speaker, Mr. Vishwajit Shon, has already joined. So please, his credentials. Hello.
Yeah, good evening. Good evening. Good evening to
Good
all.
evening.
Yeah. So I'm sharing my screen. Just keep it.
So he has, do you have his credential, that slide, or we will do it?
Now, whether you have said that the previous day I sent you, no? Same thing.
I
Yeah.
think so. Please, just a minute. কোথায় তুমি এই করো? Oh yes. Oh, আচ্ছা এই মাত্র yes. So this is the credentials of Mr. Vishwajit Shon, Assistant Vice President, Research and Development, Reliance Industries Limited, Research and Development Center, Reliance Jamnagar Refinery and Petrochemical Complex, Reliance Industries Limited, Reliance Greens Jamnagar, Gujarat. So Mr. Shon has more than 19 years of research experience in the field of petroleum crude oil refining process, specialty chemicals for refining and petrochemicals, corrosion and waste to value creation. He had an MTech in surface science and engineering. Before joining Reliance, worked in industrial R&D centers for development of anti-corrosive coatings and oil field additives, specialty chemicals, associated with Reliance R&D Center since 2008, and currently responsible for R&D activities as a group leader in energy storage systems and advanced separation technology. Current research areas are opportunity crude oil processing, specialty chemicals, waste to value creation, and materials for energy storage. He is the author of 19 patents, 4 publications in peer-reviewed journal, and 18 conference papers and 1 book chapter. He has received enormous prestigious awards: Golden Peacock Innovative Product Service Award in 2019, FIPI Innovator Award of the Year 2019, Best R&D Developed Project from Ministry of Petroleum and Natural Gas in 2018, and Best Manufacturing Process in Petchem from FICCI in 2018. I request Mr. Vishwajit Shon to deliver his presentation. Thank you very much. Please.
Thank you, sir, for your kind this introduction. So I'm sharing my screen. Just 1 minute. I think, is it visible to all?
Yes.
Yeah. Yeah, good evening all. The today's topic is this waste to value creation for sustainable development. In this topic, mainly I will cover that waste to value creations in refining, that petrochemicals refining or any refinery or petrochemicals. And last week there was a lecture on this crude oil and organic chloride, what is the effect in the refinery and challenges. I think you all enjoyed that. I was trying to make it like this so that it will be understandable to you, because most of the things you are not aware It is not included in your syllabus, or it is not available in the books and other things. So if you have any questions, you can send letter also on that. So I'll be happy to answer those questions or your queries. So now I'm going to the next. This is a normal disclaimer. Whatever I will say today, that will be my own statement on the basis of my knowledge and assessment. Nothing is related to Reliance. And secondly, that one thing I want to say about the Reliance, that new Reliance for New India. So Reliance is working for Made in India, Made for India, and Made by Indians company. The most of this earlier also, after if you see in India, the most of the technologies and other things, even in Reliance, when Reliance established, in that time also we hire or we are that good to procure or buy license from the other foreigners and foreign companies and technologies, and we are good to implement those things, technologies in India. But slowly Reliance is trying to produce, initially produce that material which is required for India, and then trying to run this company totally by Indian scientists, engineers, and other manpowers, and slowly going into that era where Reliance is doing their own development and trying to not only they commercialized it in their own refinery, petrochemicals, and other factories, but in the same time we are trying to sell that to other companies or in other countries. And there are whatever we are in the refining business, petrochemical business, and retail business, and this Reliant Telecom, Geo, and other products as well as. But in the Green India initiative, that what is going on right now throughout the globe, and India is a part of that. Our Honorable Prime Minister also announced in the last this 15th August. So in that initiative, our chairman has announced that the 4 gigafactories. So one is solar PV. We'll produce that solar PV here from the scratch. That is mostly that will be silicon-based solar PV, and then battery energy storage system, BESS. Normally, there are various types of batteries are available to store that solar energy. Actually, the solar energy is for direct for 5 to 6 hours, maximum 5 hours, not 6 hours. 4.5 to 5 hours in a day you can get directly. But for round the clock utilization of that, there is a need of the storage of that energy. So various batteries are there, but the problem pain point is that all these things are not economical. Storage cost is very high because the battery cost, though it is that slowly it is reducing the cost. And normally the market is dominated by lithium ion based battery, but it is not suitable for the whatever we are talking about your utility scale. That is, I'm not talking of the household, I'm talking about the grid and that industrial scale. So for that, we are looking mainly for these liquid metal batteries. And here this another gigafactories is a fuel cell. And the 4th one is the green hydrogen through hydrogen electrolysis by using renewable energy. So now, before going to the content, I'll say just look into this slide that in the top, take that point. Yeah, at the top it is a refining. It is that conventional refining process. So where the input is crude oil and the output is different your fuels and few petchem, and lastly it is a coke. And there is a integrations with the petrochemicals, the refining and petrochemicals Indian. The future refinery will be the integrations of all these 4. So at that catalytic gasifications will be there. We are talking about that carbon neutrality. For whatever the carbon generation source, we have to reduce that one or neutral it, or that is the one thing is the net zero, that is a neutral, but our aim and objective should be that should be negative. So whatever we'll utilize now for the net zero or neutrality we should not release it in the atmosphere. So that is the carbon capture and utilizations. and another is bio and waste refinery. So if you see there, the crude to now in future refinery, instead of crude to fuel, the main motto will be crude oil to chemicals. Why not fuel? The fuel, if you burn it, so then another in that the consumer end also we are producing CO2. That is a phase 3 CO2. So then biomass coal to chemicals. Then whatever the biomass is there and coal is there and chemicals, we have to produce all these things to the chemicals. And then catalytic gasification is another important aspect. So where we can use that all the biomass or coal or coke, pet coke, and instead of the high temperature normal pyrolysis by using catalyst, you can reduce the temperature significantly, and we can also produce the hydrogen. We'll come into that also. And second is that waste, we are talking about the carbon, CO2 is taking that greenhouse gas, all are creating problem. It is not only that CO2 captures, so we have to develop that method. Already we have developed in our R&D, Reliance R&D, and how to utilize that one and prepare the valuable product. And again, there is a green energy. Why green energy integration with that waste refinery and catalytic gasifications? Because in the catalytic gasification, what we are talking about now, the biomass to hydrogen production. So that hydrogen will be the green hydrogen because the source is the feed is biomass. And then we can talk about that bio and waste refinery, whatever the waste material is there and biomass is there, we have to convert into either is the hydrogen economy and C1, C2 alcohol, because ethanol, that your octane number is very high and it is a clean fuel, but 100% you cannot use in place of by replacing gasoline. But as per the government of India mandate, we can use the maximum 10% is a mandatory, but we are using around 5-6% as well because ethanol is not available in India that much. So the thing is that sustainability in transitions. So whatever the transition is going on, the conventional to green energy towards the green. So whatever the present or ongoing this business or industries or establishment, there is no need to set all those institutes. So how to sustain those current business? So in that transition, our mantra will be zero waste and waste to wealth or value creation. So now today's content I will discuss with the value creation from waste refinery streams. I'll give a few examples on that, whatever we have done in our R&D, and most of the things are already implemented and few things are in the line of implementation, we can say it in the pipelines. And how to sustain the plastic business without pollution. The plastic is another headache in the recent days, but without plastic, we can't think without plastic. So how to go along with the plastic, but there should not be any pollution. And agro biomass to green hydrogen, what I was telling, that one source of green hydrogen is your electrolysis, water electrolysis, but for that energy is required. If you take it from the grid, and grid is not green, your energy source is not green or source, so then you cannot say it is a green hydrogen. So that will be in a different color. There is a brown, there is a gray, there is a blue. So that will be not green. Then you have to connect it with wind power or solar power. So here we are talking about the agro biomass to green hydrogen through catalytic gasifications. And then next topic will be the waste to wealth. RCAT HTL means Reliance Catalytic Process Hydrothermal Liquefactions. It is from all this organic waste, because we have started with algae to oil. We have that this world largest pond, algae growth pond in the Jamnagar R&D Center, and our different biology group is working on that. We are in touch with them for that next part, whatever the oil part is there, and that part we will discuss, and the net zero CO2 the last, because whatever we are making and doing, that if it is not carbon neutral, then there is no use. That will be not in a use in future, a near future, because there is a mandate for that as per the Paris Agreement. So there is a waste management via waste to value creation. So waste is not nowadays and near future, that will not be the headache of every institute or any industries. So we should create value out of that. So first of all, I'll discuss with the value creation from waste stream of refinery. So this is that high value additive development from LPG Merox waste. Before going into that, I'll tell you one thing, that LPG Merox, that mercaptant oxidation. This is one of that your trade name of one company who developed that EOP, United Oil Products. They developed that particular technology, and because you know that LPG is a C3C4 materials, and it contains some other contaminants like that. One thing is that mercaptant is a pungent smell, and you have to remove it. So that's why there is a mercaptant oxidations process is there, that is called LPG Merox operations. So I'll tell you that one LPG that is initially that contains some mercaptan, as you know that mercaptan is RSH. R is any alkyl group, and it starts from that if it is a methyl group CH3SH. So methyl mercaptan is a first mercaptan, and it also contains some H2S obviously, and whatever in your household or whatever we are using the LPG gas cylinder, when you open that gas valve and knob, then there is some pungent smell, you can sense that one. So that is one kind of mercaptant we are using, that is for detection of any gas leakage. But here the content is very high, and we have to remove that one, because in that LPG the content is very ppm level, that is very up to 1 and 2 ppm, but here we are talking about it is more than that. So first step is the LPG amine treatment is there, because mercaptant is acidic in nature. So amine treatment, you have to remove first all the H2S, then there is a caustic POS to remove part of that this mercaptant. Then there is a caustic extractor where all this mercaptant is converted to, after reactions with NaOH. All these things are around 40 degrees Celsius temperature, this process, that will convert it to sodium mercaptate. That is a one kind of acid-base reactions, you can say, that is forming sodium mercaptate salt. And then the LPG will go up from that with that is mercaptan free, and then sodium mercaptide will be along with this caustic solution, that is actually any ppm level things such as 31%, and then that goes to the oxidizer. The objective of oxidizer is that now that whatever that RSNA is formed here, that is one kind of mercaptan loss, a part of caustic loss. NaOH is helping it to forming that salt. So we have to take it back. So in oxidizer, in presence of oxygen and catalyst, so there is a reaction, and it will form that disulfide oil. This RSNA, another molecules of RSNA that combine and forms that RSSR, then sodium is free from that, and sodium hydroxide again formed. So we'll get it back and recycled in the system. This is the overall that system. So why I am talking about this? This DSO is a headache of the refinery. It is a C2C4 disulfide material mainly, because both sulfurs are there, and starting from dimethyl disulfide, then methyl ethyl disulfide, then diethyl disulfide. Mainly these three components are there, and total sulfur content of that material is 60%. And the pungent smell is there, you cannot throw it out, and due to this sulfur content you cannot process even with our, because we have the sulfur removal this unit, that is a hydrodesulfurization of diesel, hydrodesulfurizations of kerosene, desulfurizations of our vacuum gas oil. But there the content of sulfur is around, in case of vacuum gas oil, it is around 3%, 3 to 3.5%. Here 60%, you cannot process this. You cannot throw it, you cannot dump it. So it is a headache of that. So to get rid of that, and it also contains some sodium, because the caustic treatment was there, around it is a 1 to 30 ppm. So we have to get rid of that. Another problem is that the sodium. So with this sodium, you cannot also process even in that small quantity with other feed. So we are thinking that how to manage this waste. And with this component, when we analyze those component, and it is matching with, it contains a good amount of this C2C4 component, it can be utilized in other ways. So we are thinking how to modify this one. And there is an opportunity. If you see, there is a this type of DMDS, dimethyl disulfide. So if you replace this R group with the methyl group, if these R groups are methyl groups, then dimethyl disulfide is formed. And normally the dimethyl disulfide worldwide, globally, it is utilized as all the steam cracker and naphtha cracker, mainly steam naphtha and the gas cracker is called steam crackers as an anti-coking agent. So during furnace, there is a coke formation that is cracked, that naphtha or any ethane, propane. So during that cracking, there is a that will form that your olefin. That saturates will form with the olefin. If you crack the ethane, that will form ethylene. If you crack the propane, that will form the propylene. So those are the precursors or for that your building block of the polymer, the polypropylene, polyethylene. So it is very, very useful material. So in this cracker, what happens, and that top of that, whatever that your furnace tubes are there. So that contained the nickel in that material. So nickel is there, and it is there is a during the cracking there is a if is a over cracking is there. Sometimes it is obviously there is a certain percentage of over cracking is there. With the desired product, we will be getting some others, and that is CO2, CO, and the last, if it is a more overcracking is a huge overcracking, cracking or significant overcracking, there is a formation of coke. So always there is a formation of coke, but within that limit. But this coke formation enhanced in the presence of this nickel in that metallurgy of that your furnace tube. So DMDS have to add as an additive because it acts as a anti-coking agent in that makes a smooth layer top of that your furnace tube, and that retard that further cracking of CO, CO2 and other the hydrocarbon to the carbon. So then coke formations to reduce the coke formations, another application is the hydrotreater catalyst. So these material, in case of hydrotreater catalyst, what we did, we have the this metal oxide, that comonimo, cobalt oxide, nickel oxide, molybdenum oxide, nickel oxide. These are combinations of those things. This type of catalyst is utilized for the hydrotreatment, because with the hydrogen gas we have to pass around for the your vacuum gas oil, heavy vacuum gas oil, that is called VGO. The VGO hydrocracking, all these sulfur materials will be converted in presence of hydrogen, that will be converted to H2S, and the material will be sulfur free or less sulfur. So for that, around 80 bar pressure is required, and around 360, 370 degrees Celsius temperature is required. So there also initially, whatever that your catalyst is, there is a one-time utilization, whatever the metal oxide catalyst, nickel oxide, molybdenum oxide, you have to activate this one. So if you pass this DMDS, globally it is the standard material, so that will be cracked at that temperature, and that will form that cobalt sulfide, because whatever the sulfur is there, that will be cracked at the particular temperatures and will form very active material, highly reactive material, and that will form the cobalt sulfide, nickel sulfide, etc. And that will be then when your material will come, then whatever the reactions or sulfur will be taken from that surface of the catalyst. So when material will come first time, that hydrogen will react with that sulfide and form H2S and go out of that column. And the next time when the VGO will pass, that whatever the sulfur compound will be there, that will be at particular temperature, again that will form that sulfide of that metal, and hydrogen will react on that. So it is very important chemicals here, and the problem of that in India, we are unable to get this one, because we don't have any manufacturing unit in India, even in Asia. We have to procure it from US or Europe. All refineries, Indian refineries, petrochemicals, they are procuring from the US or Europe. And it is that very high cost imported item, no manufacturing in India. Government regulation is there because it is one of the ingredient for the pesticides. So there is a government regulations during procurement. There is a formalities are there. Minimum 6 months is required, and to procure those things through government agencies and other things. So there is a headache. One is where to dump it, this waste material, it is not in a use normally. And these are the another problem with the DMDS procurement. So we are thinking that there is a need of development one technology to reduce the sodium content. Actually, sodium content is very high, so we cannot push those sodium content. Sodium containing, that is, though it is a 1 to 30 ppm, you cannot put these things in either your steam cracker or this hydrotreater, because that will be the poison. Sodium is the poison. Even more than 1 ppm, the spec is below 1 ppm for the hydrotreater and the cracker unit. So if it is there, that will, in case of hydrotreater unit, that is the poison for the catalyst. Catalyst is very costly, and this is a fixed bed reactor. So one catalyst for Vijo hydrotreater, if you load these things, and that will run up to 2 to 3 years. But in case of diesel and naphtha hydrotreater, 5 to 6 years or more. So if it is a poisoning effect is there, or within a 6 month time of 1 year, you have to replace those things. There's a cost, a huge cost is involved, and shut down any losses are there for refineries and petrochemicals. So we have to remove that one. So we are trying to develop that one. So these are waste to value creation. And next slide, I'll let you know how we develop that one, how to remove that sodium from that waste stream. So these are the things we have developed that one, and make these things low cost anti-coking and sulfiding additives. These are the structures of this dimethyl disulfide, and it is a mixtures of three, as I told you, dimethyl disulfide in our material, ethyl methyl disulfide and diethyl disulfide. Then we developed one adsorbent based technology. Adsorbent with this alumina, gamma alumina based adsorbent we developed in our R&D. And then in that particular this material, if we add ambient temperature, beauty of that is it is in ambient temperature operations. If you make a bed, fixed bed of that, and pass this whatever that DSO I showed you, and if you pass those things through it, and then that will that adsorbent will take all this sodium and make it below 1 ppm. What ppm it is required, and maintain all other spec, whatever the sulfur content, moisture content, and everything, that will maintain properly. And we got the patent out of that. We got the patent in US, India, Europe, Gulf countries, and Nigeria. All are granted patents. And then in our plant, we established our plant in Reliance Jamnagar refinery in 2017. There is a 1.5 ton per day current production, but total this plant capacity is 1.5 ktpa. And 2018 onwards, that material we are being utilized in our ROGC, refinery of gas cracker, whatever the gas cracker we are talking about. In our Baroda, Hajira unit and Dahej, there are three petrochemicals units are there. But here also we established in 2017 world largest gas cracker unit, ROGC. And here our feed is this propane and ethane. And we cracked it, and we make ethylene and propylene. And initially we have tried trying to utilizing the DMDS, but slowly we have, when our method was established, and then we tried it in our pilot scale in our lab, then in our pilot scale, then it took trial in our another unit in Dahej, 1 month trial, and there was a very good response on that. Then we have replaced that costly material. The cost is, I'm telling you, the cost of DMDS is around $2,000 per ton, and our material cost, though it is a waste material, some processing cost, and if we take it, the hydrocarbon value of the waste material, it is around $200. That is a 1/10 of that. So we are utilizing this material continuously till it is being utilized. And CHT, Center for High Technology under Ministry of Petroleum and Natural Gas, has taken initiative, because we presented them there, and we got the CHT award, and for this product also FICCI award, Golden Peacock award, and FIPI award also. And they took that one, and they are taking the initiative. Several meetings they have arranged, and now they want to they stop the utilization of this imported product from US all over the all Indian refineries and these petrochemicals. So this part is going on, And then we are trying to utilize in our hydrotreater catalyst. Also, we got that we send all our additive to hydrotreater catalyst manufacturers throughout the globe. All leading manufacturers, they tested it and they provided a certificate. It is equivalent to DMDS, and there will be no effect on that, the adverse effect on the catalyst. So that uniqueness of this innovation was the first time in the world we proved that up to ppb level of sodium removal. So there is no process before that, and it is significantly low capex and opex and very simple, highly efficient, because it is ambient temperature and pressures. Only you have to pass it through that column, and that bed you can, whatever our scale is there, you can utilize it up to 6 months. We can regenerate it, but there is no need because it is not costly that much. Regenerate cost will be more than that. So you can reject it, and then new batch you can put it and run it. Very green process, and our additive is being tested in HPCL R&D Bangalore, and for the hydrotreaters and other crackers, we are working on that. And this is that there is a licensing opportunity, because many companies we are talking about to license in the other places, and also the cheapest alternate of BMDS and savings for foreign currency. This is the thing, and indigenous technology, we can say it from concept to commercialization in India, and only by the Indian people. So this is our commercial plant or particular these things. So now next topic is that how to sustain the plastic business. The plastic is the headache, but we cannot sustain, or our life cannot go without plastic as on today. So what we developed that one process that is called the plastic circularity, and it is also the circular economy. That we have developed one method in our Reliance R&D, that is sustainable catalytic conversion of waste plastics to stable oil. We are preparing one stable oil. So why we are talking about stable oil? Because this oil, if you heat it, that is one kind of the pyrolysis, you can say, the high temperature. If you crack those things, the plastic materials, and that will provide you the oil along with some gases. But those oils, because the most of the plastics, if you you know that those are the polymers. So majority of that PVCs and other thing, polythene that prefers as a monomers is the olefin. So when you will do that things, the olefinic components will be there in the oil. So if it is the olefinic component, the stability will be the another issue. It will be easily oxidized, and gum formations will be there. So there is a spec for in the gasoline and diesel also, the gum formations. So that part, to avoid that part, and we have developed one things and one novel process, and that is the green catalytic pyrolysis process, and that it can take all kind of plastics. Because if you see in some literatures and in the net, Google also, it is available, various processes are there, many people are doing in the small scale also, many places it is going on. But whatever you can get, that cannot process all plastics. But in our process, we can put everything, every type of plastics. The next slide I'll show you. And in the multi-layer plastics, multi-layer means there is a whatever our I can give you examples on that. Your biscuit wrapper, and in your potato chips and other things, whatever the wrapper is there, the inside there is an aluminum layer is there. So this is for multi-layer type of plastics, multi-layer film plastic, MLF. So those things also you can process in the same process. There is no need of segregations. So this is that I'm taking you in that there is a screw feeder for the plastic feed, the chopped and cut plastic feeds. There is no need of any segregations, only small species are required. That there is a clean rotary clean reactor is there, the negative pressure we have to maintain, and there is a heat exchanger. Through that the gas liquid separator, that paper will be there, then the gas liquid separator will be there, there will be liquid product, and so few gases product is there, and we'll get some char plus catalyst. So everybody is talking about, many companies and develop, many organizations and R&D centers, they have developed that plastic to oil. But these oil are not suitable for any use. Any use means directly you cannot use it. Then you have to go for again refine those things. The different boiling point, the cut points you have to do it. There's a naphtha, then you have the gasoline part, then light kerosene, and maximum up to diesel range you can get it from there. So as a whole, you cannot use it. So there is another process is required. So then there is another problem is that oxygen content of that. There is a limitations and specification for oxygen content, olefin content in gasoline and diesel. So all these things are there. Then there will be some other pretreatment. So that will be the costly. So what we are doing, we are getting, I think in the first day, my senior colleague, Mr. Sukumar Mandal, talk was there on multi-zone catalytic cracking, MCC. So that MCC can take all kind of this feed, that is hydrocarbon feed, any crude oil or any oil, and that will give you the BTX and these olefins, so benzene, toluene, xylene, and ethylene propylene. So we are trying to put these things, whatever the oil is there, instead of again distillate it and make it that things, and there will be some spec related issues with some other contaminants and ingredients. It is better to put these things in MCC, whatever we have developed, and then we will get that ethylene, propylene, benzene, toluene, and xylene, and those are the precursor for the again the plastic. So there is a circularity. If you put it, distill it, you process it in along with the refinery feed, then again you will produce some fuel, and again you will burn, and that will generate the CO2. But here, that will not be there. So just see there, here the mixed plastic feed, even weight also, if it is a soil, there will be no issues. And it is whatever the oil we are producing, it is a stable 80% stable product, 80% yield we are getting. Any kind of plastic, PP, LDP, HDP, PS, PVC, anything you can put it here. It is very cost effective, this process. Smooth operations, we have tried it up to pilot trial we have done, and now this we are working for the demo scale trial. And here you can see that this thing temperatures is around low temperature. This pyrolysis, catalytic pyrolysis, we have developed that catalyst. It is proprietary catalyst, and there is a temperature up to 450 degrees Celsius. And the negative pressure system is there in that rotary kiln, and the low acidic stable liquid product we are getting. So eliminating agglomerations, leakage, emulsion formations in that product, the low cost reusable catalyst. The catalyst is reusable. It is along with the char, you can segregate and you can use it. So this is the process, and we are getting all kind of things. And this is our pilot scale product. We are getting, this is the crude oil after getting from plastics. And then we distill it out in the lab scale true boiling point TBP unit, true boiling point distillation unit. It is the equivalent to our commercial distillation unit, mini scale commercial distillation unit. And then we are getting this light naphtha, middle naphtha. Light naphtha means it is up to 150 degrees Celsius. It is up to 150 to 165. This heavy naphtha 165 to this 220. This is 180. This is 180 light kerosene to 225, 27, and this is heavy kerosene 227 to 25 to 270, and diesel is 270 degrees Celsius cut to 370. So these are the product we are getting. So whatever we are talking about already, Mr. Mandal described that things. And in normal crude oil case, if you put these things in normal way, refinery configuration, this is CDU, crude distillation unit, vacuum distillation unit. This is atmospheric distillation unit, which is called CDU. Some places it is ADU. This is vacuum distillation unit in FCC, fluidized catalytic cracking, and this is delayed coker, DC. So then you will get fuels and feedstock for petchem, means ethylene, propylene, that part we will be getting. So that is around 10 to 15%. But if you go by this process, the multi-zone catalytic cracking, you will be getting more than 70% of this part. That is, instead of 10 to 15, that is 70%. So there is around this ethylene is more than 20, around 20, it is 33%, BTX is 14%. So we are talking about the plastic circularity. So if you if we catalytic pyrolyze those all plastic and make it the oil, crude oil, and then pass it through it, and then whatever we are getting, this is ethylene and propylene. This is the precursors, and also in some plastics, there's benzene and other components are also required, toluene and xylene. So these are the precursors of the your polymers or plastics. So we are getting back. There is a circular economy is there. So MCC is a process that can transform fuel-based refinery to petrochemical plant. So that will help in the circularity of the plastic. So this is the MCC process already. Few part we have discussed here, and we have demonstrated it in our refinery, and now we are working for the commercializations. Then we'll talk about the agrobiomass to green hydrogen. So whatever the normal green hydrogen route is your water electrolysis. But for that, that electrolyzer, this is the process is costly right now. Commercialization is there, but hydrogen cost is very high due to that processing cost. Whatever the platinum cathode is being used there, and there is a septum is there, and whatever the overall cell cost and corrosivity is another issues. You have to change those things. So the overall cost of the hydrogen is very high. So right now it is not economical if you compare it with the normal hydrogen generation through the SMR, the steam reforming in another. So then another process, and again you have to connect it with the renewable energy source, either solar or wind. Otherwise it will not be green at all. That will be some other colors. So then how to alternate of this one is the agrobiomass. If it is the agrobiomass, if we process or gasify it catalytically. Why we are talking about the catalytically? So all this agrobiomass, the waste product. So waste, you see in that Haryana region and whatever in the Punjab and Haryana, when they after that their cultivations and all other things, when they cut that their crops and whatever that rest over things, they burn it, and that is creating problem in that Delhi area. Huge pollution. That is your PM level was very high, particulates matter. So those things are that really the headache of the society. So instead of that, if we gasify this agrobiomass, this the pyrolysis process is available, but our process is catalytic. So catalytic means we have to reduce the temperature significantly. Our method is requirement is less than 850 degrees Celsius. So agrobiomass availability in India is a 220 million metric ton per annum, and we can produce it around 70 million ton per annum syn crude through that if we process it. So here I have taken I told all these points that we have filed 3 patents on that our method, and we required less than is a low temperature process if you compare with the normal gasifications, thermal gasifications. So that is more than 1000 and 1100 degrees Celsius. It is 820, and we can through this process we can utilize as a feed agrobiomass, any coal, pet coke, any kind of biomass, and 100% conversion of pet coke also. Pet coke is the end product of the refinery, that whatever that vacuum residue is there in the delayed coca unit, that is converted to 30% of that vacuum residue will be converted to the pet coke, and remaining will be then this other petroleum products, fuels and others. So and another is that whatever normally it is that when it is not a particular feed basis, because normally we use that mixture of that day I told you, the mixture of a blend of crude oils. The 30% average, it is thumb rule, 30% is that your vacuum residue, and 30% of that vacuum residue is the pet coke. So this expected benefit is that it is around 40% lower capex and opex versus conventional thermal process, and it is ideal for high as Indian coals. I think you are also aware about that. Whatever the Indian coals are there, it is a very high ash content. So that's why there will be some issues with normal coal gasifiers also. The ash content will be very high, the ash deposits and other process related issues are there if you process high ash Indian coal. But in our process with the catalytic gasifications, you can easily use high ash Indian coal. There will be no problem, and you can convert all these things into methanol also. So either you can process it to hydrogen mode or methanol also. So these are the things, and Niti Aayog shown clean interest on that, demonstrating this technology. Already pilot scale we have done, and we had discussed with Niti Aayog also, and the demo run we are preparing for the demo run. So this is the process. Here, this is a gasifier around 700 degrees Celsius. We are utilizing this one. We are pushing steam, and this is the coke or any biomass, anything you can take it here. And then whatever the catalyst is there, after that is coming back to the regenerator, the combustor chamber. And then there is around 820 degrees Celsius, you can get it back, its catalyst. So then you can put it catalyst here. So this is the process, and that whatever the CO2 is there, CO will be getting that syngas, actually CO plus carbon monoxide plus hydrogen, and then with that you can produce that with the catalytic process is there, and you can produce the methanol. So that is the eco-friendly gasoline component. We are talking about the methanol economy also. And see the difference between these two. Whatever that this is the catalytic process and this is the non-catalytic process. Whatever the end product we are getting, the tar and other things, that clear zero tar. Our process, whatever the catalytic process is there, that will produce zero tar. And here this is what the condensed steam we are taking, and here it is a non-catalytic, that is a thermal process direct, and we'll get that this type of tar. The bottle is a transparent bottle, but due to the oil material and tar, it is looks like the brownish. And what another advantage of this catalytic process, we are getting 10% more hydrogen than this non-catalytic process. So catalytic biomass gasification is a zero tar process. So that is another advantage. And why we are talking about green hydrogen, because we are getting 10% more hydrogen by this route. And if it is a biomass, if it is a coal, we cannot say it is a green. So if it is a biomass, then that will be the green hydrogen. And there is a comparison between the catalytic and thermal process. This is agro biomass and highest Indian coal. The two feedstock. There is a thermal and there is a catalytical, thermal catalytical. If you compare these two, this the capex part, if you this is for methanol production, calculated 1 ton per hour methanol production. If it is a Z, suppose any amount Z is that capex for to establish that plant, this much amount money is required. Then for catalytic, it is will be the 64% of that Z that will come down. And here also the same thing. That is in catalytic process, that significant reductions of the capital cost. And that payback also, if it is a capital cost is less, if you use this cash cost means whatever the production cost, the production cost is also less. If you see here in the catalytic process, the production cost is A, here it is A plus 2. So this type of advantage is there. Just see that temperature and pressure, 1500 degree for thermal and 45 bar. Here it is 780, less than 800 you can say, and 4 bar. So huge difference is there. Your utility cost will be lower. So that's why the cash cost is low in case of the catalytic process. And the payback, due to that your capex is less, and the payback means whatever our investment is there in how many years and how rapidly or quickly I can get it back. So that is called the payback. So in case of these, it is a 7.5, 8.1 years is required to get it back. So here it is only 2.6 and 3.6. In agro biomass, it is a little bit more than this one. So we are renewable hydrogen rich syngas, we can get it. 250 million ton per year biomass will provide the 60 million ton per year syn crude, whatever that availability in India. And next, I'll tell you the waste to wealth. It is waste biomass to any product, that is organic feed. So that is in the genesis of that. In our case, algae to oil production is there. Whatever that bio oil we are trying to produce is from algae. So just like a jetopa and other feedstock in any grains and other things, it is algae. So we don't want to take that the food grains and other things. We don't want to waste food. So algae is the safer for that. And jetopa initially that was started, but oil content is less. But here the oil content is more. So genetically modified this our biology group is there in our R&D. They modified the gene and they produce the algae, and we cultured those algae, and algae growth is there in our own ponds there, and we are getting more oil by modified the gene modifications from the particular algae. And after that, what we are doing, we are producing oil. So this process we have developed, it is called RCAT, Reliance Catalytic Hydrothermal liquefactions. So this HTL process is known, hydrothermal liquefaction. What we did, we developed one catalyst, and entire the process economy has changed. So this is the beauty of our project, and it is not only restricted now to only algae. Now whatever our process is developed, it can take any kind of organic feed, agro waste, municipal sewage waste, food waste, that is your kitchen waste, food processing waste, manure, biosolids, ETP sludge, effluent treatment plant from any industry, industrial waste, mixed non-recyclable plastic, automobile waste, tires also we can utilize this one. So this is the part of how to waste handle and then those things. And then any organic part you have to take, and other inorganic part you have to reject it here. And then with the feed conditioning is there, and then heating you have to, it is go through the heat, the chopped feed. And then with this process, with the catalytic system, with temperatures, that after that, that filtration will be there. So biochar will form from that, and whatever the gas and some liquid, that will be collected and separated out. So that is the totally green crude oil. And then there will some treatment is required, because if you know, if it is a form, various components are available ingredient. If we talk about the algae, it contain, because the plant this contain more potassiums and huge content of cellulose, lignocellulose, that contains oxygens. So in the crude oil or any kind of oil, oxygen content, as I told you earlier also, oxygen content, if it is a more, and that will easily oxidized, and that will create problem in that system. And olefinic content is not required that much in the feed, so that will form that your this grease formations and gel formations, that will create problem in the engine. And so we have to do some pre-treatment on that in the existing refinery infrastructures. So then that will produce the jet, diesel, and this MFO, fuel oil, marine fuel oils. Whatever the top part is there, the heavy end will be utilized as a marine fuel oil, and the jet oil, biojet, and biodiesel will be able to produce. So I think you all know that about the biodiesel, because from other source also biodiesel is being produced. That is whatever that our from that vegetable oils we are getting. All other triglyceride. A triglyceride means this is that your alcohol plus acids. So this is from triglyceride, because glycerol, the alcohol is glycerol with 3 hydroxyl group. So that will whatever your C6, C14, C15, C16, C17, C18, all these acids are available in that oil, vegetable oils. So in that process, that will be converted to the ester, methyl ester, that is the biodiesel. So here we are getting that biodiesel directly from this, along with jet and MF. We are not converting it, but that is in the diesel range material. But we have to remove all the contaminants from that in the existing refinery. So 70 million metric ton bio waste in India, it is available. We can get 20 million metric ton bio crude. Some gases will be there, some biochar will be there along with that. So it is a green solution for towards growing energy demand, the waste as a resource. So we got the Golden Peacock Award for this process. So what are the opportunities there? If you see the global scenario, the MSW food, STP sludge, agro sludge, how much is there? 1,000,000 tons per annum. And if you put this process and arc at HTL, then green crude, you can take 4 to 5 billion barrel out of this. And with the existing refinery refining process, you can get it. If you process these things in existing refinery along with this or separately, along with the existing oil or separately, you can get this aviation. So this is called nowadays SAF, Sustainable Aviation Fuel, the jet fuel, and other transportation fuel, diesel you are getting, and the marine fuel, MF, will be getting MFO. The Indian scenario will be getting 300 to 400 million barrel this of oil, and the global is 4 to 5 billion, and we will be getting this 100 to 140 million barrel this ATF demand. So this is the process, and this process is that eliminate the CHG, the greenhouse gases and all these that can eliminate directly, that will produce the biofuel. Because if it is a catalytic process, the temperature is less, the gas production will be very minimum. And we got 35 plus patent on that. Not only this technology, this processing, this after processing, before the gene modifications of the algae and other process. So overall, the patent portfolio is 35. And we are developing the tested in various feeds for industrial sludge, ETP sludge, the kitchen waste, food, this municipal waste, sewage material. So there is an enormous business potential for this. So it is a very good example of this wealth, waste to wealth. And if you compare with this other bio-CNG, 2G bioethanol, all these things are in the bio is the feed, and 3G bioethanol, that is catalytic gasification with syngas conversions. What I was telling, that is by catalytic gasifications of biomass, you will be getting that synthetic this syngas and syn crude, and then you have to convert it to ethanol and methanol and RCAT HTL, this process. If you see here, that anything here is a dry is required, here wet feed is required, here wet MSW dry, anything you can take it. But anyway, that will be wet because we have to utilize water in that. And then what is the capex? You can see there, it is the capex are more. Here it is a low 0.3, it is higher 0.9. But if you see the profit, it is a 3 times of that. And payback is 2.6, here 3.1. So overall, if you see that main product, here it is giving in the same type of feed 133 this kg per metric ton of feed. Here we are getting 500 kg per metric ton of feed. So if you see all over these things, so it will be more better than the conventional, the bio-CNG and other processes. So next, this is the last one. Quickly, I'll finish that one. So we are talking about all these processes, but unless until we another waste material nowadays, it is a very headache for all globally headache that we are going for that net zero or carbon neutrality or all sources. So unless until we do that one, so there will be no usefulness of other method or processes. So there is a net zero options is there. One option is low cost CO2 capture. So whatever the sources are there, we can capture it. So we have developed one process that is hydrated solvent process, and direct air capture is also in that. It is available. This process is also scientists are working on that. Otherwise, there is a commercialized carbon capture process, CO2 capture process is there. It is amine based because it is acidic in nature, so amine solution easily that can take it. But cost is high, and some these corrosion related issues and other issues are involved. If you compare with our process, it is a sorbent process, hydrated sorbent. The CO2, then we have to capture. After capture, we have to utilize. So we can make it chemicals, the ethanol, formic acid, urea, otherwise dimethyl carbonate and methanol economy. If we prepare methanol and dimethyl carbonate, those are the fuel components. You can use it in gasoline. that concrete curing purpose, you can utilize it. That will form that certain alkali metal, alkaline earth metal carbonate. In that basalt rock mineralizations, you can CO2. This is called utilizations and sequestering of the CO2. In the basalt rock, you can put it that CO2, and that it can be inside that rock that will be captured. And so one thing is here capture, and then after capture, what we have to do to make it net zero. Then underground sequestering, it is work is going on in the seabed, under the seabed and the other, but the risks are involved in those things. So in those two things, people are working on that. And CO2 to biofuels and renewable. There's algae to chemicals are there. So we can, whatever that algae we are growing, we can, CO2 can be utilized as a feed for that. CO2 plus renewable power to fuel. So whatever the hydrogen we are getting in the green source, we can utilize with that, whatever the captured CO2 and make it a fuel. So waste plastic to oil, and then bioethanol is there, used fat to oil, waste cooking oil to fuel. These are the all to renewable oils and bio-based oils. So recycling plus circularity for sustainability equal to zero waste. So whatever our topic is today, that zero waste is that the future. Either we have to make it zero, or if it is there, we have to take it as an opportunity and convert it into the wealth. So this is the last slide, and how we have developed that one with hydrated solvent based CO2 capture process. And this is a carbonate, mainly the potassium carbonate based adsorbent. And here, if we pass it through, suppose the flue gas is there, the flue gas contained 160 degrees Celsius temperature. This temperature is there 1 bar. If you pass it through that your heat exchanger, because it is here, it is required initially, that will go here, and at 80 degrees Celsius it will absorb, our adsorbent will absorb CO2, and then that will be dissolved at 130 degrees Celsius, and CO2 will be released. You have to capture those things, and then your bed will be utilized for the next run. So here, why it is a very, very low cost? If you see the 40% lower OPEX than conventional amine route, and operating cost is 40% lower. Why? Because here we are doing the heat integration. So it is coming around 160 degrees Celsius. See here, in one bed it is required adsorbent bed 80 degree, and desorbent bed it is 130. So these heat we are utilizing nicely. Here we got patent for that heat integrations and adsorbent development. So there is no need of external heating. So it is a totally eco-friendly and green process, you can say. We are not using any other sources for heating. And we have compared with the other method, and our the capex is 70% lower than the conventional amine route process. We have done the pilot study, and now we are working for the demonstration. And then after that, we'll establish our own plant. So thank you. This was the last slide. If you have any questions, because it is too late, yeah, another I took 12 minutes more than the specified time. If you have any questions, I'll take it, or otherwise you can send it through the Swamiji after that, so we can interact on that. My email ID and phone number is already with him. Thank you for listening. Thank you very much.
Thank you, Mr. Vishwajit. This is a really wonderful presentation with full of new ideas. In fact, those are the academicians working in the, conventional field. Many of the things are very, very new to us, and definitely for the students, these are really important, innovative ideas they can think of. Any comment from Oshanandada? Oshanandada, are you here? Hello.
Yes, sir. Yes, sir. I was listening quite attentively, because many of the things I was interested to know also. Because these are all in the research phase, I understand. But it will have a very bright commercial future, that what you have explained. That's why I was very much interested to know. And I was listening attentively, sir.
One part is already commercialized, the first one, that is disulfide oil. That is already in 2017, we have established our plant, and 2018 onwards, we are utilizing instead of that commercial additive. We are utilizing since that, yeah, continuously. In our own plant, we are utilizing.
What is the capacity?
Capacity is 1.5 KTPA. And it depends upon that how much in your crude oil, that is in the feed, how much sulfur is there and how much mercaptan is there. On that basis, you can get. It is fluctuating. So whatever we are producing right now, we are utilizing in our own ROGC because it is a big unit, world largest refinery of gas cracker unit in Jamnagar in our complex only. And we are trying to send it to our other, because our objective is that first of all, we will be utilizing in our Reliance, whatever that requirement is there. Then we have tie up with this associated with the CHT, and they are taking it for that other Indian refinery and this petchem. Because the objective is that make in India slogan is there. No? So whatever we are procuring, it is 10 times more higher cost. And foreign currency is going out, and we don't have any this manufacturing unit in India. So they want to stop that activity. Yeah. So that's why we have started that one early, and other things are in the pipeline. All are almost this your pilot study is over. And MCC is in the final stage. Already, Mr. Sukumar Mandal already presented first day, and it is in just we are working with our project group for the first commercial demonstration unit. Most probably within 1.5 years that will be established in Jamnagar.
MCC, I mean that is required for biofuel to hydrogen also, green hydrogen also.
No. MCC is required is there crude to oil,
only, no?
crude to oil, and another part is that waste plastic, whatever the oil will be producing, if you put it in that MCC, that will give you the circularity. Instead of again producing fuel, you can get that ethylene, propylene, BTX.
Actually, you have shown one slide, biofuel to green hydrogen, no?
Yes, biomass to green hydrogen.
Biomass to green, yeah. I am just a little confused in the sense that nowadays the color of the hydrogen is being given based on, I mean, the electrolysis requirement. I mean, the source of hydrogen has been given mainly from electrolysis of water or from splitting of methane.
SMR, steam reforming, yes.
Yeah, these are the two basic source of hydrogen.
Yes.
Is there. And if it is from electrolysis, then what sort of energy is being utilized? If it is the renewable energy where carbon footprint is not there, then only it is known as green hydrogen.
Yes.
That is what we are seeing right now. But in case what you have shown in your biomass to green hydrogen, whether it will be still remain as green hydrogen or not.
Yeah, actually, whatever our, I think you are also aware that 3 years back we have commissioned 10 gasifier in our Jamnagar complex. The feed is that this coke, petroleum coke, pet coke. But we are getting hydrogen, CO2, CO. All we are getting from that. So these hydrogen are not green. This is your gray hydrogen. And with our
gray also is not telling actually now.
SMR that will be gray.
Actually, it is talking about actually what is
Turkish.
Yeah. Because green and the blue they are telling that renewable energy is not there. Energy is there, but CO2 is captured.
Yes, but that's why we have developed our CO2 capture method. And we are working on that utilization of that captured CO2. Then that will be blue.
So maybe your terminology what you have used right now for biomass to green hydrogen, that might have to be changed actually.
Biomass to that is pet coke to hydrogen, that is not green, but biomass to hydrogen, that will be green because your source is biomass.
But they are not saying green is associated only with the electricity of water.
No,
That
it
is
is not like
nowadays
that.
terminology is
Yes,
like
yes,
that.
change. It is changed. That
It
is
changed
any
actually.
biosource, if you take it from the bio, that is, if you, it is from algae, or if it is any this food
Any
grain,
materials basically, vegetable materials.
any biomaterials, plant, then it is a green.
That was early. I don't know. I mean, just we can go through again the literature.
Because
Maybe
recently, last
maybe,
month, I was this present in that one in World this Renewable Energy Congress. Last month it was there. So there is a 2 days conference, and the ministry level was there, and there was discussion was there. One the session was there. Dr. V.K. Saraswat was there for this hydrogen initiative. That part, the last session. He is in now this taking care of this green hydrogen initiative from the Niti Aayog. So this part was discussed. This bio route is
because
the
now color of hydrogen is being given based on the production,
yes,
and mainly from water electrolysis or methane splitting.
yeah,
And based on the energy, whether it will be from coal or renewable or
yes,
with CO2 capturation or
yes.
nuclear, they have got all colors. In fact,
Yes,
except white color, white is the original hydrogen. Otherwise, they have put all color: black, gray,
yes.
pink, turquoise, and all those things.
But if you see that water electrolysis, if you compare with SMR, steam reforming, it is too costly.
Yeah.
Due to that, this your platinum electrode, and
exactly.
work is going on that non-noble metal, because we are also associated with some other the research lab. We are working together to develop some non-noble metal electrode, so that your cost will be reduced.
Electrolysis cost will be reduced.
Yes, yes. So that work is going on.
But a lot of new concepts have been deliberated. Although we definitely would like to see the commercialization, as you are saying that it will be close to that, because there a lot of technically as well as commercial benefits are there.
Yes.
So thank you. I hope let us call the session.
Yes, yes. Yeah. Actually, here also in total Saurashtra region, heavy rainfall is going on.
Oh, I see.
Yes, yes. Today, because our things now due to COVID situation, either you can come office or this thing. Due to some activities, I came to the office. But that day, I attended from home. But now it is heavily raining outside. I have to go home. And some of that I have heard that some of that highways also they have closed. So all these things are going on. Yeah.
You are in colony or?
Yes, yes. I am in township. That is the outside of that.
I know. I had gone there. I had stayed there. In the guest house, I had been there. In your guest house.
Yeah.
Okay.
Okay. Thank you. Thank you very much for inviting us.
Yes. 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 Surely.
Thank you, sir.